All right, so we've tackled series circuits and parallel circuits, and those are fine. Those aren't super hard. And probably the most difficult ones for students to kind of get their mind wrapped around is what we call complex circuits. And so complex circuits are really just series and parallel circuits combined together, and this is typically what you're going to see in an electrical circuit. Very rarely are we strictly parallel or strictly series. We're generally some combination of both. So how do we attack these? How do we approach these from an analysis point of view? Well, it's very important to understand or to be able to identify what the simplest part of the circuit is. And so when I say the simplest part of the circuit, I mean what are the series parts and what are the parallel parts. So here, hopefully it's easy to see, but maybe not. But we have a parallel portion that is right here. And if you can't really make that out, let me just cover up everything but the parallel portion. And so now we see we have a path coming into this segment. It splits into two, as a parallel normally does. It has two paths for current to flow, so current would flow down here or back the other way, really doesn't matter. And then they come back together and flow back to the battery. And that's going to be our parallel circuit. So what do we do with that? Well, before we get there, let's redraw this, and maybe it will be a little bit easier to see. It's kind of hard to see in this looped configuration here. Let's redraw this to maybe visualize this a little bit better. So I'm going to take the positive part of the battery. I'm essentially going to separate the battery here. We're going to view it from a different perspective. So we're going to take the positive part of the battery, and I'm just going to represent that up here. And so as we leave the positive side of the battery, the first thing that we encounter is the R1 resistor. And so we're going to leave the battery. We're going to encounter the R1 resistor. And so I'll just sketch this in here, and it has 5 ohms. And the next thing, as we leave the R1 resistor, we get to this segment here where we diverge into two different paths of current flow, one going to R2, one going to R3. And so we'll sketch that in as kind of a T or a Y, right? And so it Y's off, one going this way, one going this way. And so here we have one going this way, one going this way. And then we'll just sketch in R2 over here, R3 over here. We'll just say R3 at 5 ohms, R2 at 5 ohms. And then when we leave R2, we hit this point, and then when we leave R3, we hit the same point, and so we have to join these two back together to the same point. And there we go. After we leave that point, we end up going back to the negative side of the battery, and so we need to represent that as well. So we'll go back to the negative side, and we're just going to represent that as a ground symbol. And so what this symbol means is just the negative side of the battery. It's electrically connected to the negative side of the battery. And so now it's maybe a little bit easier to see that R2 and R3 are in parallel with one another. And then what we do from this point, from an analysis standpoint, and I won't get into the math in this video, is that we're going to find the combined resistance of R2 and R3 in parallel. And from our last video, we know that any two resistors that have the same value that are in parallel, we can just divide by the number of resistors. And so 5 divided by 2, because we have 2 of them, is going to be 2.5. And so we represent this parallel circuit as a fake resistor, sometimes called a representative resistor, right there. And so we just take those two and combine them into one. And if we look at that circuit, we see that, well, now that's just a series circuit. I only have one path for current to flow because these paths disappear, and we just get this path right down this guy here. What do we call him? So we can call it really whatever we want to, but it's the total resistance of this parallel circuit. And so I typically call it like an RT, and we'll say prime. All right, and so the little vertical tick mark is the prime symbol. So we'll just call it RT prime. And so what's the resistance of RT prime? Well, it's the resistance of R2, which is 5 ohms, in parallel with R3, which is 5 ohms, and that's going to be 2.5 ohms. And so RT prime is 2.5 ohms. And so with that, now we have a series circuit, and it's R1 in series with RT prime, which is just a representative resistor. Remember, it's representing this overall circuit here. And so this series circuit is going to be R1 plus RT prime, or 5 plus 2.5. And so our true RT, our R total, is going to be equal to 7.5 ohms. Okay. Now, that's one type of complex circuit where we begin with a parallel circuit first. This is our simplest circuit. We don't have one resistor coming after another one on either of these legs. And let's maybe see another way to view this. As we leave the battery and we come out here, we hit this junction first. And when I hit this junction going this way, I know, well, that's a parallel circuit. That's not a series circuit. So maybe the parallel circuit is the first, is the simplest type of circuit. Well, let's leave going the other way. If we go this way, we hit a resistor first and say, well, maybe it's a series type of circuit. So let's go through that resistor. Well, we get to another junction here. That junction then diverts into multiple paths of current flow, which by definition is not a series circuit. And if we go this way, this is multiple paths of current flow, which is not a series circuit. They both lead into each other, and so that's how we get that parallel circuit. Let's look at a different type of very simple complex circuit, which would be this guy right here. And so this guy, give you a second to kind of look and see if you can determine what is the simplest circuit. And so if we leave here, we see a junction, right? If we leave here, we see a junction. And so your mind might go, well, that's a parallel circuit. That's the simplest type of parallel circuit. But if we continue on, we only have one resistor on this leg before we get back to our junction. That's good. We still haven't broken any rules there. It's still a parallel circuit. But as we go down this leg, we see that we run into R2 and then R3 right after it. And so we have a single path of current flow between R2 and R3. And so this single path of current flow right here is a series circuit, and it's embedded in this overall parallel circuit. And so right here is the simplest circuit. And if you tried to find the overall resistance of the parallel circuit, let's say this leg in parallel with this leg, you would have to do this math first before you could then do the math to get the parallel circuit resistance. As the same as you did up here, you could not get the series because our last calculation was a series circuit. You could not get the series values without first getting this parallel value to be able to add to this single resistor up here. And so the first thing we have to do down here is find the value of this series circuit. And so series circuits, we just add R2 to R3, and so that's going to be 5 plus 5 for a total of 10 ohms. And then we represent this leg of the circuit as a representative resistor, just like we did before. Now, a thing about sketching in our representative resistors that is very, very important, I'll finish doing this here and then we'll explain it, is that we have to sketch them in a very particular way. And the rule for that is that we have to begin our representative resistor where the circuit that we're replacing begins, and we have to end it where the where the circuit ends. And so in this case, our parallel circuit started up here at this junction. This is where it diverged into a parallel circuit, and so that's where we need to connect it to start with, and then it came back together down here, and so that's where we need to end that representative resistor. Here, the series started right here, and so I can connect it really anywhere on this portion, and it goes through the resistors, and then it ends down here, and so then I can connect that representative resistor anywhere down here. These are two different points of potential, just like these are two different points of potential. This point and this point actually have a voltage across them, and so does this point and this point. It has a voltage across it. So that's just on sketching in representative resistors. Again, this is R2 plus R3, so this is going to be 10 ohms represented as RT prime. And then if we cover that up, we can now see that that's just a simple parallel circuit where we have R1 in parallel with RT prime. And without even knowing what the value of that is right off, we know that it's less than 5 because the total resistance in a parallel circuit has to be less than our lowest resistor. And so without knowing the exact value, we at least know that it's less than 5. So punch that into our calculator. We go 1 divided by 5 plus 1 divided by 10 equals, and then we're going to take the reciprocal of that, and that gives us a RT of 3.33. And all I did there was I took the reciprocal of 5 plus the reciprocal of 10, and then took the reciprocal of that value, and I came out with an RT of 3.33. And so RT is 3.33 ohms. And so what this means, and when we collapse all this down, is that if I looked at, let's say I took a multimeter, right? And let's pretend these are multimeter leads for a second. I got a red one, I got a black one. And if I were to put a multimeter lead here on the positive terminal and a multimeter lead here, and I was checking resistance, what my multimeter would tell me is that the total resistance as viewed from this point is 7.5 ohms. If I viewed it from, let's say, this point, it would read between the meter, right? It would just be reading this portion here. And so it would read 2.5 ohms. Okay? It doesn't know what's, the individual things that are going on in here. All it knows is that between these 2 points, it's 2.5 ohms. So I could literally take these two out and replace it with a 2.5 ohm resistor from here to here, and it would read the same thing. No difference. If I go down here and I put a multimeter lead here and a multimeter lead here, and I'm checking for resistance, the resistance right here is going to be that 3.33 ohms. Because again, it doesn't matter what's going on in here, it's just whatever the meter is seeing looking back this way. So I could literally take a 3.33 ohm resistor and connect it from here to here. The meter would read the same thing. Here it's going to read the same thing because I'm still touching the same points of potential. However, if I read across here, now I get that 5 ohms of resistance. If I read across here, I'm going to get that. I'm still going to get that parallel because I haven't disconnected this portion. I would need to disconnect this portion to make sure I'm reading just between the two meters. Otherwise, it's going to have a path to go here and a path to go here. It's still going to read that 3.33. But that's a little more when we get into using meters. So that's without any calculations. Total resistance here ends up being 7.5 ohms. The RT prime resistor, which is just the combination of R2 in parallel with R3, comes out to be 2.5. Our small series circuit here, which is R2 in series with R3, comes out to be 10 ohms, and we call that RT prime. And then we combined R1 with RT prime in parallel, and so that's 5 in parallel with 10, and that comes out to be 3.3. Next video, we will get into some calculations and talk about how we work this analysis getting real values. All right?